Yeah, so I demonstrate how to run on real devices backend using the V2 version in Qiskit runtime service estimator and also sampler. Here the code listed on the slide was still V1. We know the difference of V1 and V2, right? V2 you need to use the pub. When you run the job, it's not circuit, it's list of tuple. And inside each tuple, it's circuit, depending, okay, this is estimator, so you will have observable, and then you have this also the parameter if you have, so maybe I put it here. And then also have the accuracy. Insert here in estimator 2. Run. You will need to input people, circuit, observable. Observable can be a list, observable. And then parameters can also be a list. And then this accuracy. Should be here. And if you have more, then you have more tuples. And sampler too, when you say run, you have circuit. Sampler, there's no observable, so parameter and shot. Okay, this should be tuple. So list of two. So you continue with other second, etc. And here is V1. This is V1. Okay, so we going backward. Yeah, this is the slide from Dr. Saran about various simulators, primitive, runtime, etc. Because we've been talking about these two type of primitive. No, two type, like two primitive, estimator and sampler. They're the two primitive, but two type it means V1 and V2. There are some differences that we see. Right here, this is still V1. Right? You can see the way they provide, right? List of circuits and shot. This is still V1. That's why looking at the input, circuit also. Yeah. Okay. We also talk about session and batch, right? That's the diagram for session because you need a classical post-processing. And batch is similar, but you don't need the post-processing because one job to the other job, there's no relation between them. So you just pack all the different circuit you want to run. We talk about the resilience level. This would be using the options. We also talk about building noise model, right? Maybe a few lectures ago. Yeah, so you can have a noise model. You can actually get it from the back end. And this is for simulator. So this backend option has this noise model. You can build it. Okay. So this is import additional error without deploying error. We use this in previous. You have the probability, different probability, and apply to the add right. Add all qubit quantum error, deploying error, right? And this the probability. This is the number of qubit. Remember this CX. We play with this noise model uh, a few lectures ago, and this is the readout. Readout is just saying that uh, if it's zero, it has some probability to get measured zero, but it can also be measured one with this bit flip, and a state in one can be measured with small probability zero, and large probability to stay is one. Here they are assuming the symmetric. Like the bit flip is always the same, but you could have zero flip to one less and one flip to zero more because one would be the excited state, so it would decay more to the ground state. And ground state is have less chance to be excited to the excited state. It might also be other mechanism causing the bit flip. Yeah. So let me not do the bit flip here. Yeah, today we're going to look at a code that use classical feed forward. What does it mean? Like this CF. We remember we talk about CF is used in when you measure register and I would want to use whether 0 or 1 to do something. But this is actually deprecated as we have seen in the warning of the code we used previously. So now we use this with if test. Yeah, to do the things. And this is actually in the homework, right? This is in the homework of teleportation. Let me see if I have the code. Yes. Okay. But the way to write is with if test. This is the test, and then you do something here. Okay. And I want to mention there are other control flow like switch, while loop, and for loop. Yeah, we did homework 3 teleportation. We use if test. Let's go to the documentation. This is the documentation for the classical feed forward and control flow. If statement, we just mentioned that if test. If you want more detail, you can click this. Tell you how to use that. There's example here. Maybe you can take a look at this. Qiskit circuit, import quantum circuit. Okay, qubit 0 bit. So yeah, so we used to have the quantum register and then classical register. Now that in this example, this is something I never used before. Qubit, classical bit, and bit, the list of qubit, 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 classical bit, classical bit. And then you construct this quantum circuit. This is interesting, so I want to copy because I never use this qubit construction and classical bit. Let me open. Okay, okay, new file. Classical. Okay, yes. Copy that. So let's draw the circuit. Draw the circuit. Right. So this is use this. This is very interesting. Right. Use qubit. Three. There are three qubit. So this is how. And there are two classical bit. The ordering is really just from zero, starting from zero. So 0 to 2, 0, 1. And you can just say I want to construct circuit using these bits. Bits can be quantum or classical. Hadamard on 0, control now 0 and 1. And you measure 0, quantum bit 0 to classical bit 0. So you measure 0 to this. I mean, these, you all know this. Okay. And then you also do the Hadamard. Yeah, so this is after the measurement, you can still do Hadamard. And then 0, 1, another 0, 1. And then measure 0, 1. Okay. So, and there's additional things with quantum circuit that if test. Okay, this if test, you need to specify the checking condition. Bit 3 is 0, 1, 2, 3 is a classical bit 0. And if test if it's 0, you do a X gate. If this is 0, you do X gate. Wait, sorry. There are two measurements, right? So the first measurement outcome is at bit 0. Second measurement is at bit 1. And here we are using the classical bit 0 to do that, right? So it's here. If this bit is 0, then you do X. If not, if it's 1, okay, then you do a Hadamard and then Z. So you can see if else. If you want to have else, you will need to say as else. Otherwise, this will be just the if part. Okay. Oh, how do I undo that? With if test as else, right? That's the okay. Okay. So this is the circuit, and we can simulate using, for example, air simulator, or you can run a real device. But this is just showing that straightforward. This is from the document here. Okay, oh, I can also just copy this. this. Which one is, yeah, this one. Okay, I just wanted to just put out the source of this. Just put it here. Yeah, they're more detailed here. So that's not, it's not necessary to go to such a detail. There's also the switch. It's useful to get from the code. And I'm just going through this simple code. I think we learned from the example. Okay, now this time they use the standard corner register, classical register. So you have 3-bit in the corner register, 3-bit in the classical register. Yeah, and you construct this circuit. You do the Hadamard on all the 3-qubit, and you do the measurement on all the 3-qubit. You could say measure all. Here you can also say measure all.
Yeah, switch case.
What is
No, switch case.
switch? Yeah, so we're looking at switch. So switch, you say with. It always these kind of statement. With something, with QC that switch. Classical register.
How do we get like 2, for example? Oh, because it's like measure.
You see, as case with case 0, x.
It's
uh,
1, 2.
Oh, case 1, 2. How many registers do we have? Case, okay, case 0, case 1, 2. Other. Okay, so we can look at the documentation here. Oh, I accidentally clicked that. Close that. So that's Google. Google is, what is that? Search switch. Qiskit. Which case is this? There's still some. This is different. It's like switch case operator. I don't even know this one. A circuit operation that execute one particular circuit block based on the matching target. Is it switch? What's
I think it's like reading the whole classical register as one like number or something like that.
it's possible? It's like one, 1, 2. Let me see. Uh, let's just go back to the switch. Oh, I have that. I have the link. So this is case 0. This is probably treating everything 3-bit. It's probably 0. Integer case 1, 2. If you have 1 or 2, you do this, right? Yeah, and then the rest you do control not. So this is probably treating the 3 classical bit as an integer representation. Okay, let's see if they have an explanation. This is the switch. Yeah. If called with all argument, it will create a switch. Oh, this is a switch case operator. Operation. That's the it's a class with the given instruction. If cases and Q are not passed, this then acts as a context manager, which automatically builds a switch. And this one you do not need to keep track of. Okay, there's example here. Case. Okay, iterable tuple. Any 1 second. A sequence of case specified. Each tuple define one case body. The second item. The first item of the tuple can be either a single integer value, the special value case default, or a tuple several integer. Each of the integer value will be tried. In turn, control will open, then pass to the body corresponding to the first match. Match all possible values. Okay. Each define one case, second. Single integer. I think this is saying, yeah, if it's 0, if it's 1 or 2, yeah. Okay. I might have that actually. Maybe I might have I'm redoing this. There's more. I was saying I might have a notebook. Let's see. This is one download from the. Okay, maybe this is easier to. We have covered if test and switch. We can. Yeah, it's similar. Yeah, they use on the register. U0, C0. Okay, this is here, right? They use if test. They don't have these else. So C0 at 1, okay? This is if this is 0. 0x1, okay? Then this second example is what we have, similar to what we have as else. If you want to do operation in the case where this is not certified, you need to use as else. Okay. And comparing, you could also use this 0B, 001 binary. Okay, switch. With circuit, switch C0 as case. Yeah, 0 or 1, so it's easier here. Right. But here you could also use the binary and this, right? So this here is clear, like the binary 00 or 011.
This
In
is like the whole class.
the whole, yeah, in this example, it is zero, the binary 001 or 010 here. Yeah. Let me see. This is how you read the documentation, and then you could get the example from there. Run. Uh, let's go back to the documentation page. Oh, okay. Because the documentation, they might have something interesting, like they write the bits in that way. Okay. Next will be while loop. There's example. Here, let me copy this. This. That's for the fun. Right. So in the end, we always like putting the display of this circuit. From here, from here, from the circuit plot, you see that the case is 0, the case 1, 2. They don't use binary. We could say, right, as we just learned, we could say 0B001 and 0B010. Okay. And let's just plot this again. Okay, it still says 1, 1, 2. This is for the while loop. They still use this qubit classical bit. Okay. With QC, the while loop, and you check the condition. If the condition is satisfied, then what? Keep doing that. If bit 2, that's the classical one, is 0, and where do we get 0? In the beginning will be, I think we'll initialize to be 0, or the bit will be initialized to 0. When quantum state will also stay 0. Initially it will be 0, so this would run. And then it would apply Hadamard, apply C0, and then measure this. So if it's 1, then it will stop. Right. So when it's 0, it will continue to measure. Okay. So this is more like a classical, usual these control. Classical. Where is the documentation? I think it's here next to. Okay. So this is for the while loop. The next one. There are more detail than we can cover here. Look at this. I measure. Oh my. What's the other one? There's one final. Okay, it talk about a lot of things we covered before. Remove final measurement, measure all, etc. I don't see the other one. There's another. Oh yeah, here. Oh, this is it's tell you how to do the remove final measurement.
So it's like clearing the register.
Yeah, only the final one, but somehow we don't need here, right? This is not somehow the documentation just keep going and then go to some other things. Did we miss while loop, right? We didn't miss any. Okay. Okay, so maybe we go back to this documentation. This is the for loop. Somehow I didn't see the for loop on this page. Let me check for loop. For, there is one. Okay, it doesn't seem to give oh, there is one. Okay. Somehow we missed this one. Oh, okay. Anyway, we found it, so I'm going to copy this. This. Well, you can learn from many places. Okay, we already imported current circuit. Okay, for loop, that's plot this. Then make it so that each block of code can work. Okay. And you see some warning. See if it's fabricated. Okay, so here will be an exercise that we do here. Okay. So this is a for loop. We see this in range 5 with QC dot for loop range 5 from 0 to 4 as I is classical index. Somehow I is not used here. I suspect maybe you probably does not need this if I remove as I still because I is not used. Okay, quantum circuit, it would apply Hadamard, control not, measure 0, and 0. QC dot break loop. Okay. So it would run from 0 to 4, but if you want to break, you could also break loop. See if 0 true. Okay, so what should we do? Now we see this deprecation. What do we need to use? Let me scroll up to the first one.
Okay, like with
If test, right? If test. Okay, so let's change this to if test so that warning goes away. If test. Okay, so what should we write? This. So it's qubit as classical bit 0. Is there a name for that? And if it's true, we usually said 1, but let's see if it instruction set. Let's see. QC dot this if test. Did I write it correctly? Oh, break loop, right? We will need to do this, and then we say break loop. QC dot break loop. Oh, we need to use with what? With if test, yeah. With if test. Right, this is a good exercise. We just is that correct? With QC dot if test. I think that's right? Okay, let's see whether it accept or not. Runtime warning, see register bundle set to false for instruction need to refer to individual classical wire. Okay, so it's better to define classical wire. Usually you have a classical register for it, right? You need to have, here they use bits. You need to give a name. You could also use C register. C register equal to classical register. There's only one, and I'm defining this as CR, and I want to use CR. You could also say CR1, I guess. Yeah. But it does not like PO has to be both. Yes, we need to have on the register. I think you have to use register or integer, but you cannot mix both. Just we should have. I mean, if this code block to work on its own, we should import that. But we have import that above. And let's see, and more. We don't need
There's
this.
only one classic register.
Yeah. Oh, or I should use 0. Yeah. Right. Makes sometimes use. Okay, different. Yeah, different. What's this R0? Oh, range 0, 5, 4. And this is if it's 1, then it breaks. And you could also use 1. You could also use 1. Or you could use 0, B1, I guess. Or 0x1, according to they have, right? You could also use 0x1. Let me just 1 or 0x1 or 0b1 or true. So there are a few ways to write. Okay, that's for that one.
Does that mean we run the circuit for 5 times? Like the loop?
No, not the whole circuit. It's like here, this block will repeat. All right, this is the zeros one would run, and then you would have.
Do you repeat it for 5 times?
Yeah, you will repeat 5 times, but because
break it.
Oh yeah, I understand.
I will break it but if it does not break, then it will run 5 times. But any
So the
part of
diagram
it
is just one block.
here is to 1 block. Yeah, that's probably the best way to represent it. You don't want to copy and then each time it says for this. I think that's already pretty good representation of the well look, yeah. So whenever you need to test, you will need to have the register has name. The classical register need to have C bits. You need to have them with names. And then when you construct circuit, you cannot mix register and number. You use either or number or register. But we learned that you can use qubit, CL bit, and then call them as bits, and then you can construct a quantum circuit. Yeah. For loop, we just see that. Right. So as right, I was not needed. So this it underline. I'll just go back to that part. I is not needed. As I. Let me just write it. This is really Python, right? If you don't need it, just I don't know. Okay. Okay. While loop. We already seen the while loop. Okay. So we're done with this. Classical feed forward. When we see that actually I have this homework. We go to homework. What's my homework? I think if I'm done with this this semester, maybe I'll put the code on GitHub or something. Maybe not a homework. Maybe not a homework. Because then every year I need to come up with new homework problem. Okay. There's a there's a FIFO part. This is CF classical register 1 and this like you have come to this homework. Maybe you haven't. Okay, that's okay. You're great then. Okay, so I so ask because there's a 4B. For A is using the old one, if CF, and here is using the with QC dot if test. And you write just like that. We have gone through this. I mean, we seen CF, we also see if test. I introduced this earlier, but this time I just emphasize them. Right? So you have even you have seen all these before the homework, but you learn it on your own, going through that, and then we emphasize again here. Okay. So this is the precursor to this notebook we're going to look at today. I don't know whether I upload that. If not, I'll upload it now. Do you see that on the website is L07D? If not, let's check. I can check this. Check that. No book. So no, there's no 7. I'm going to upload that. Let me upload. Add a module. Is script. Okay, I'm uploading. Select file. You don't see my action but on screen, but I'm doing it now. Document 605. So I need to copy from the Linux part to the Windows, and then from Windows upload. Right, so you'll see that appear. Nice. If you refresh, there you go. Right, so there's no bug. You can download. Okay, so I'm going to open that and use the other computer to share. Okay, so this is using the CIF or even switch allow us to do something interesting. It's called dynamic circuit. And you see that in the teleportation. Okay. So this is not, yeah. So let me go through this. This is also in, yeah, there was video. If you're interested in watching them. Right.
The quantum research community has already identified a number of applications of dynamic circuits.
Dynamic circuits.
These examples span quantum error correction, quantum simulation, quantum machine learning applications, and much more.
Okay, so I won't go through the detail of this. I won't go play the whole video, but I'm going to through the notebook in detail. So one thing is that this has been recognized that you could do measurement and then do feed forward, actually allow you to realize some task faster than entirely unitary. So for example, creating a GZ state. And we know creating a GZ state, we have seen notebook on that a few times back. I mean, remember we also compare like maybe this one, Hello World, like how efficient the simulator. Let's see if this is the one. Yeah, this is the one, right? GZ state. Yeah, you see the circuit depth. If you do it like this, it's really a proportional number of qubits. But you can actually do something else by creating some other entangled state with ancilla, and then you measure out half of the ancilla, and you'll be able to create the GZ state with depth 1 or depth 2, constant depth. Doesn't matter how the system size. Okay, and there are also other ways, and there's long range CNOT teleportation. There is a long range CNOT. There is a paper. I should probably long range CNOT. I think there is a Nature paper associated with it. Okay. There's one, but then there's another one. So it's by Elisa Boimer.
This one, the one that they gave in the talk some time ago.
Where is it?
This picture.
Yeah,
right
this
there.
one. This one.
Yeah, I think it's this
Yeah, that's this kind of picture. I know there is a nature paper they implement this and with similar diagram. Yeah, so these kind of long range CNOT. Right? If you have to do unitary, you kind of need to do some kind of swap. But you could also use dynamic circuit. You see this, there's some maybe small number layer and then Hadamard measurement. There are a lot of these double green line, these representing the classical information. And plus is logical addition. And then you do this here and there. Okay, so this I think we can read more detail later, because we have been here just going through notebook, but we can also read the paper. Last year we were reading a lot of paper. I don't know, you remember? Last year we read more. Last year
last year
605. Yeah, because that was the first time I taught this. Yeah, so we can read more detail. So this semester is more practical. The last semester is combined, last year. But we can come back and read this. It will also be useful for the final project. Okay. There is I remember there is a nature paper. I can search. Long range something. Boimer. I learned that this is pronounced as Boimer, not Baumer.
Oh.
Boimer. She said that. Thing is nature. Okay, there is this. Yeah, there is a. Yeah, she gave a talk. It's good. This maybe I should. This is the talk given by the author.
Good morning, everyone, and welcome to the IBM Qiskit live quantum seminar series dedicated to you, the research and academic quantum communities. In just a minute, I'll be thrilled to roll out an episode one. And tell us, since you do globetrot quite a bit, where are you?
I'm happy to dedicate today the full seminar just on that. As Dr. mentioned, anytime you have some questions, please just put them in the chat and I'm very welcome to.
Yeah. So what I'm going to do is I'm going to copy the video link here. Oh, no, this is not one. Yeah. I'm going to say there is a video by Lisa. I don't know how to put it one out. I would say this is highly recommended. Yeah, so this is the link. Okay, so the first is to map this circuit problem to the circuit, map the problem of long range CNOT to the circuit and operator. Let's take a look at this. Okay, as usual, you need to enforce on circuit register, classical register, especially you want to do the feed forward. Oh, and there's also things that we have not mentioned as using this expression. expression allow you to do some logical operation between this classical register. I don't know whether in my teleportation homework I have that or not. This is the no, this is the home. Yeah. But we're going to see that here. Okay, this is the homework 3 teleportation. Yeah, I haven't had homework 5 yet. So at least you get a break for that. Let's see. Yeah, so I think when I was designing this, I was using these, I was trying to use some of this feature of expression, but it's okay. We will learn from here. So this is what Dr. Wang did here. So this 1D chain of nearest neighbor. So you need to find eventually, right? Like last time when we were looking at these GSG state, you find a path, a linear path. So there's a 1D chain of nearest neighbor. Okay, so zeroth qubit is define the problem, is the control, and the last qubit is the number of qubit minus 1, the index, is the target. The control qubit starts in the float state. Of course, in the paper, you want it to be, can be arbitrary state. Arbitrary state. Let me just open this here. This will be our reference. Okay, so let's take a look at this. I'm not going to explain this. The paper would derive that. So you have control knot like this, and Hadamard, like Hadamard on these like 0, 2, etc. And then followed by like pairs of the C knot, and then another C knot, but so switch translated by 1 qubit. Okay, and then you do the Hadamard on the one that you have not done the Hadamard. Of course, control and target are special. Then you perform measurement, and you have classically control Z. This is perhaps to get rid of some extra phase. And then you have these classically controlled X. This is to flip the bit. Okay, it would explain here. A circuit for a long-range NOT gate spanning one-dimensional chain. You only want to use the nearest neighbor because that's what's used in the circuit. In the middle is equivalent unitary. Okay, right. So the circuit depth is proportional to the number of qubit. On the right, this is equivalent using the dynamic circuit, using measurement with feed forward. So this is called dynamic circuit. The circuit depth is O1, right? It doesn't matter how many qubit you have. It's always this structure. If the post-measurement state is unused, feed-forward operation can be handled in post-processing, eliminating the need for the experimental implementation. They say, okay, they have additional common yellow region indicate idle time during CNOT and other qubit as well during measurement. So remember, if we have this, we can do the dynamic decoupling, right? We can apply like XY4 or X something, right? In these idle period. Okay, so that's the implementation. Number ancilla equal to number of qubit minus 2. Well, because you want the control and target, and these are the two that are not called ancilla. The ancilla pair will be number ancilla divided by 2. It's because this kind of structure. If you want to call this pair, if you count this as pair. Yeah, but for this circuit, you have to pay attention to the even and odd between the two. But yeah, let's not worry about that here. So corner register, classical register, CR1. So this is number of ancilla pair called CR1. The parity control XK. Okay, let's look at this diagram. So this will be this darker green was from here and maybe the next one here. So every pair that is this result, and they have to do the plus, the addition, a logical addition or binary addition. Okay, so this is what's needed. And then CR2 is number ancilla minus other ancilla pair. Well, isn't it okay? There is a mod, so they may not necessarily be the same because there's a mod 2 integer. But that's not worry about that additional one. Parity control Z gate. So CR2 will be from these, right? That the lighter green that would do the control Z. Okay. And CR3 for the final measurement on the control end. CR3 probably would we can just or the final measurement. Okay, this is the final measurement on the target and control. What that means is here, once you have a control gate finished, you want to measure the control and target. Okay, it's not the measurement is not here shown here because it's just implement that control. But to verify, the CR3 just provide you the final measurement on the control and target. Okay. Now this is the quantum circuit. Right. So we just explain different register, but essentially it's corresponding to this structure here. It's good that I opened this paper and the diagram. Otherwise, if I just look at the code, it's hard to understand, even though they have some circuit in mind. Right? Even looking through this, we already learned a lot with the help of this diagram. Okay, so you initialize the qubit. The 0 qubit is the control. You want to initialize because it states that the control is you want to start in the plus state. Okay, a draw barrier, entangle control, and the first ancilla qubit. So remember that structure, control and first ancilla qubit, right? That's here. Create belt pair on ancilla qubit. The first ancilla qubit in index 1. So there's the belt pair. So if you look at the structure, this is creating belt pair, right? Hadamard and Sina, right? Creating 0, 0 plus 1, 1. So there is a structure like these pairs. So this should start with index 0, 1, 2, 2, and 3. Let's see. So 0, right? Start with 0, be 0, 2 plus 0. So 2 and 3, right? And then pairs, number ancilla pairs. And then prepare bell pairs on stagger ancilla and data qubit. This would be C naught and Hadamard. So in range, so still with I start with 0, so it'll be 1 and 2, and then Hadamard onward. So let's look at this. This is this one here. 1 and 2, and then Hadamard on 1, right? You see this structure. So this is like regular structure until here. Yeah. In a sense, this is entangling. This is entangling these two. Okay. Okay, and then measurement on alternating and still keep it starting with the first one. Keep track of the parity or eventual. Control Z gate. Okay. This is you're going to measure. Let's see. It starts with 1, so this is 2 minus 1, so it's 1. The qubit 1 is going to measure and store in the CR2 zeros bit. Okay. Qubit 1 is measured. This one's measured and stored in CR2. So CR2 is associated with a Z. Double check again. Yeah, this is control Z, right? CR2, parity control, Z gate. Okay, so this is a trick. This is a trick that I thought I had that in the teleportation, but I think teleportation is too simple. There's no need for doing any logical. Okay, so what it uses is this expression, EXPR. It's allow you to do the classical addition on your classical register. Okay, so if I equal to 1, the first one, you will say the parity control, you assign parity control to this expression. If you expr dot lift, you lift this CR I minus 1. This is the first one that I stored the classical the measurement outcome in this classical bit. Okay, if this is the first one, you store it, you lift that into some expression okay. What about the next one? The next one, if I measure, then I would just add, right? So the add is I would say parity control becomes the parity control and do the XOR with the next one that I measured, bit XOR. Until the end, you get the value. Does that make sense? I hope it's clear. It's this diagram here. You use this EXPR and you lift this outcome, okay, and call that a parity control. And then you measure the second one and you do the XOR. XOR is a binary addition. And you do the XOR until here, the end. And then this can be used to do the classical control Z gate. So next step will, of course, will be the X. So measurement on stagger, alternating, and so the qubit starting with the second. By starting with second, I can say, okay, here I equal to 0 will be the first one, so it'll be 0 plus 2. That is going to store in CR1. Okay, the second qubit counted from 0. Second qubit counted from 0, 0, 1, 2. This is measured, and then you will lift that to an expression. So you can do the XOR with the following measurement outcome, right? So you say parity, but this is control, and this is target for the target. Expression lift this register, so I can do the logical operation. So this parity object will do the bit XOR with the next measurement outcome. Okay. And then you say with QC, if test parity control, then we'll apply the Z gate to zeros qubit. That's shown here. Right. Oh, I also want to maybe copy the paper, the link of the paper. This is here. So here. And the other one is doing the X. Apply to the -1 is the last register. Okay. And then at the end, it measured zeros qubit, last qubit, and store in CR3, 0 and 1 bit, right? That's all here. Okay. Good. Let me just modify this. It is highly recommended. To refer to figure 1. I think they have a Nature paper, but I couldn't find it. Figure 1 and this paper. Let me execute this plot. And now let's plot this circuit with just 7 qubits. Right? We see the structure. Right? If you just flash back to this diagram, this is the same one as this. This is an example with 7 qubit. So you create the entangled pairs, right, pairwise here, and another, the alternating pair here, and you perform the measurement. This perform a measurement, and yeah, and these two are added, right? That would also allow you to apply the control X. And these qubits measured to the CR2. Yeah. So this is an example that the number of qubits is R. So that's why this CR2 has 1 more bits than CR1. Okay. We didn't talk about the detail of this even and R, but this is shown here. Okay, so this will be expression. The expression is doing all these XOR, and if it's 1, then you do the Z. Okay. Okay, this is a 41 qubit. Okay, so here what's doing is the maximum number of qubits 41, and it start from 7 qubit to 41. This is skip 2, right? So you have a lot of circuit. Then you collect all these circuit in this QC list. Right? You construct this dynamic CNOT circuit and running through all these number of qubit, maximum 41. Okay, yeah, of course if you want, you can print out one of them. QC list. The last one was 41. It's going to be a large. Okay, let's do this. And then let me say folding. Okay, going to be a one really long. Okay. Right, and it can even fit within the circuit depth, right? The circuit depth can actually fit within the screen, right? If you, of course, we use a small And I ask it not to fall to another line. So I use fall. But you can see it's constant depth. The only thing that make this looks longer is because of measurement. But all the measurement can be done at the same time, right? Yeah, this is not the correct representation of the ties. It could be because these measurement looks like a staircase, but they can be done in one. Okay. So the optimize, right? We have learned how to do the optimization. Optimize the problem for quantum execution. We use preset task manager, and this is selecting these. Oh, I think in the video he used Cusco, and I was using the IBM Marrakesh. Okay, and you need to transpile. We know how to do that now, and you become an expert after the group presenting this task manager in more detail. Circuit optimization. You execute the circuit, you see that it used V2, right? V2, and it's doing the sampler. Sampler meaning that it's doing these control. Ideally, it's a control gate applied to the first 0 qubit and the last qubit, right? And you start with the qubit being plus in the control, like you have this. And then the 0 qubit is 0 to begin with. So last qubit to be 0. So the output state should be 0, 0 plus 1, 1, right? And you want to measure and to see that that's the case. Okay. So suppose I ran this. I'm going to retrieve the job and then append the results. Oh, then so it's counting the probability. So it's a Bell state. So you see the data extraction here, it only extracts the CR3, it counts, gets shots, and then you count number of 0, 0, and 1, 1, and divide it by the total count, and treat that as a success probability that you get the Bell state. Of course, it's not. It's just, yeah. There might be phase difference in others, but it's doing these sort of effective probability. And you append this to this, and then others is probability of not getting the pair. Okay, and we're going to plot that. Okay, so I'm retrieving, so it would take some time. Once it get all the data, I could plot it. And yeah, so this is the outcome. This is the probability of creating a Bell pair with the distance. There's a distance. You would expect to drop. You would expect to drop as distance, but different qubit has different error, and different link have different error. So it's not necessary that it has to decay. Yeah, explanation. I would expect, but there are also these before. We had a video, right? You can just see. I think what he get is very
But note that the
monotonic.
dynamic one achieves the same result with
So this dynamic. So he's explaining this as I did. Yeah. So you could also watch through the video. It's essentially what we did here. But with me replacing him explaining this, I'm sure that the one explained much better. And he wrote the code. It's amazing he wrote code real time. He wrote the code real time. Right? You can see I was just downloading. I downloaded his notebook. Okay, now he's explaining the result. Okay.
So let's pull those up and show you the results of running these dynamic circuits on real IBM quantum backends.
He's using Qiskit IBM.
So step 4 will be to do the post-processing.
Okay. See, he
And
really
plotting.
writes real time. It's amazing. A lot of lectures, IBM lectures,
Over every
they do
circuit
real
within
time
this
coding.
sampler bash. Now let's create some control and target qubit. Like,
Okay. 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 You see that.
so here are results. On the x-axis, we plot the number of qubits. Remember, it started from 7 all the way to 41 qubits, over which we're doing this long-range CNOT gate teleportation.
Okay.
On the y-axis, we have the probability.
So,
The blue color is getting a 0, 0, or 1, 1.
Yeah.
While the orange color is getting some other result. And you see all the way up to 20, 25, maybe even 30 qubits, we have probabilities that are quite different from each other, indicating some success of this
okay. And you see the experiment that I ran says 20, 25, right? This is on a different machine, same code. So this machine is much better. This IBM Vericache is much better. Like, and even a 40 qubit away, it still is very good. Like 60% versus 30 something, right? It's pretty good. This is a machine that has a high gate fidelity. Yeah. I just want to flash maybe what the machine is here. Compute resource. This is probably the best machine. And you can see these Heron version 2, R2. These two probably are the best machine. This is not so bad. And I think this one, IBM Sherbrooke is going to, maybe these two are going to retire soon. Not sure, yeah. At least I know Sherbrooke is going to retire. But you can see, maybe Dr. Wang's lecture was how many years ago? 1 year or 10 months ago? Okay, maybe 1 year ago. And you see a different machine has a different, right? This is very impressive, I would say. Yeah. So it's looking good if they keep improving. And with error correction, etc., being possible, then I think this is very promising. Okay, so I'll end today with this. Any questions? With this impressive result. Okay. So I'm going to close the. See you on Monday.